Okay.
Hi, Amy. How are you doing?
Hi, sir. Yeah, I'm doing well. How about you?
Very good. So last time we looked into how do we approximate some values of sine, cosine, and tangent of a given angle, right? Are you clear about that concept?
Yes, thoroughly. I've done many questions from my book.
Mhm.
Makes sense about the small angle approximations and everything. So yeah,
Mhm.
there was actually one part within that exercise
Mhm.
that was dealing with percentage error in your
Mhm.
approximation. I don't know if we covered that, but I just kind of left that. So I think we
Yeah,
could go through that
yeah.
today.
Correct. So we learned the concepts about why do we do that kind of approximation, why
Mhm.
those formulas are there. So we derive the formulas also, correct, for sine,
Right.
tangent, and cosine. Now today we look into percentage error, as you had mentioned me on the WhatsApp about it. So I prepared the lesson for you. Let me share the lesson, and then we'll discuss all kinds of questions based on percentage error.
Okay.
Now, can you see my screen?
Yes, I can.
Can you read the title?
Okay. So small angle approximations and percentage error.
Yes. So that's what we are going to do. And that's exactly what you need, right? Now, I hope you remember this particular graph, which is on the left side. Y equals to X is a line in the center in red, correct?
Yes. Yeah.
And then we have sine X and tan X graphs, sine X being slightly lower than the value of X, and tan X is slightly higher than the value of X, especially when we're talking about the region where the angle in radians is very small, correct? So
Yeah.
especially in this part, let's say when radian angle is kind of less than 0.5, it is pretty close, sine, cos, and tangent values to x. The approximation formulae I've mentioned here, sine theta is approximately equal to theta when theta is measured in radians. Similarly, tan
Yeah.
theta is also equal to theta. For cosine theta, we can work out using the formula 1 minus theta squared over 2. We derived all these formulas also in our last class, correct? And I hope you understand the complete concept behind it. Now it is a question of just calculating. Now, when we calculate any particular value, we should be also knowledgeable about what kind of errors are we, getting across doing these approximations, right?
Yeah.
So I'd like you to just look at the graph and then just tell me if for a particular angle, I mean, let's go back to the screen. Yeah, can you see the screen? No?
Yes, I can.
Yeah, okay. So if let us say, if I take an angle of theta, let's say theta is equal to, let us say 1.2 radians. So if theta is 1.2 radians, this is one that is 1.5, if it is approximately here. This is 1.2 radians from the graph, right? So I will approximate sine theta as what value? Sine theta will be equal to 1.2 and tan theta will also be equal to tan
1.2.
1.2. So both are 1.2. So because sine theta is approximated to theta and tan theta also is approximated to theta when the angles are very small. Perfect.
Right.
The exact value, however, for sine theta is lower than 1.2 as you can see in the graph, right?
Yeah.
However, tan theta is higher. Perfect. Now we are looking into percentage error. Percentage error, standard formula, the calculated value, which is in our case the approximate value, minus the actual value. Actual value will be on the graph of sine and tangent, right?
Yeah.
Divided by actual value times 100 gives you the percentage error.
Oh,
Is that
right.
clear to you? No.
Yeah. Yeah.
So that means the difference in value between the actual and the estimated divided by actual value times 100 will give us the percentage error. So that becomes a standard formula for percentage error. Clearly?
Yeah. Yeah.
Now, can you tell me for any particular angle theta, Which will be better approximation, sine or tangent?
The sine x is
Yeah, sine x is
from
very
your graph.
close. Right.
Yeah, very
So
close.
sine x is better. Actually, we can say this is like far better, right? This
Yeah.
is not that good. This is not that good, right? Another thing which you notice is which will be negative percentage error and which will be positive. Can you tell me that? For tan theta, will it be, if I calculate percentage error, will I get a positive value or negative value? We are approximately at this point, right? So this minus the actual value.
Yeah.
So
Oh,
that
so
will be
it'd be positive.
negative, right? So because
Oh.
approximated value is lower, right? For tan graph is above. So that is the value. So that minus this. So we have a negative value for tan, but we have a positive value for sine theta. Is it clear to you? Because for sine theta, the approximated value is higher. So approximated value is higher, right? This is plus something more, right? Actual value is on the graph, which is lower than y equals to x. Is that clear to you?
So the approximate value, where do you get that from? The graph or no?
Approximate value is the value of the theta itself. So in this particular case, the approximate value is 1.2, right? Use your calculator and tell me what is the actual value of theta so that we can find the percentage error when theta is equal to 1.2. Let's do this calculation, right? So approximate value is 1.2 minus actual value. So put it in radians. So shift mode in my case, 4 is in radians. So if I do sine of 1.2, I get a value which is
0.93.
0.9320, right?
Yeah.
That is what I get. Divide by 0.9320, right? So let's calculate 1.2 minus this, 1.2 minus that result, divided by 0.932 times 100. What do you get? You get
28.8%.
28.75%. Yeah, 28 point. So that becomes the percentage error for a value which is 1.2 radians. Is that okay?
Right. Okay. Yeah.
28% is pretty high. Let's try to see. 1.2 radians is actually how many degrees? Can you convert that?
Yeah. So 1.2 times 180 over pi.
Correct.
68.75 degrees.
68.75 is a huge angle. Do you understand?
Yeah.
68 is like a huge angle. So even with that 68 degrees, we have an error of 28%. Correct. So if I would have taken a degree, so that gives you an idea. Well, this is pretty high value, right? It may look small for radian measurements, but actually it is 60 or almost 70 degrees, correct?
Yeah.
But see, even for 70 degrees, the error is around 30%.
Mm-hmm.
So we have an estimate. It's not that bad. I mean, normally we are saying very, very small means we'll go for 10 degrees, correct?
Right, right.
So there it will be very, very low error. Perfect. So that is it. Secondly, you also notice that this was positive, right? Because the estimated value was higher than y equals to x is above the sine graph, correct?
Yeah.
If I would calculate same place, error for tan theta, I'll get a much higher value, correct? Because try to do that. So for tan, 1.2 minus, what is the tan value? First figure out what is the tan value.
2.57.
Okay, 2.57. So you do 1.2 minus 2.57 divided by 2.57 times 100. What do you get?
Minus 53.4%.
See, almost double, right? Do you see that? Because clearly, because that particular gap is much higher than the gap for sine. Is that okay?
Right.
So two things which you learned just now is while calculating percentage error for the same angle approximation, tangent theta will give us higher error than sine theta, and tangent theta value, percentage error, will be positive. And that calculated for sine theta will be negative, since y equals to x is a graph which is between sine and tangent, right?
Yes.
Okay. So that gives you a very good idea to answer many of the multiple choice questions or many questions in the test paper. Only this much of knowledge. Do you see that?
Yeah, yeah.
Okay. Now, let us also look into the cosine function, right? So I have graphed this. The parabola is the approximation 1 minus x square over 2, where x is the angle.
Right.
And the green graph is actually for the cosine function. You can see that the green graph and the red graph matches over a period of much longer time. You see that? And theta. So percentage error while calculating for cosine will be very, very low.
Oh, okay.
Correct?
Very
Second,
accurate. Yeah.
very low. Estimate value is lower than the exact value. Therefore, since it is lower, just as in the case of sine, we'll get negative percentage errors. Is that okay?
Yeah, yeah.
Okay. So this is so based only positive percentage error will be for tangent calculations, correct?
Yeah.
All right. Now, normally when we say percentage error, we may say absolute value of percentage because we are actually interested in how much error, whether it is positive or negative. Sometimes we are not so concerned about, right?
Yeah,
So
yeah.
we at times also use the term absolute percentage error. So then in that case, we'll just calculate and then write its absolute value, which will be always positive. Is that clear to you? Okay.
Yes.
So this is the foundation for calculating percentage errors, and we did some. So now let's go through the examples. So I'd like you to do the calculations as we see the examples, right? So here is your very first example, which is, can you please read this question?
Yeah. So the percentage error for sine theta for a given value of theta is 1%. Find the ratio of sine theta to theta.
Correct. So multiple choice question, 1% error. 1% means one more, right? Sine theta will be one less. Sine, which is higher? Sine theta is higher or theta is higher? This is theta, right?
Yeah.
And that is sine theta. So
So
in
it's
the multiple
sine
choice
theta is
question, what do you
lower.
think is the right answer?
Wait, sine theta is lower on the graph than theta.
Yes, sine
So it
theta is
has to
lower. So
be-
the numerator will have a lower value.
Yeah. It
And
has
in
to
the
be.
denominator will have a higher value, correct?
Yeah.
And if you want only 1% error, we are very close, correct? 1% error. What will be the right answer out of these? That is a multiple choice question. That is correct, right? 1% means one more, correct?
Yeah.
Out of 100, one more. So that means this is your right answer. You get the idea?
Yeah, yeah. Okay.
So this is just from logic. We don't even have to do the calculation. This is the concept of percent, right? 1% of 100 is 1, right? So, so the calculated value is 1 higher. So it is 101, right? And because of sine theta over theta, theta comes in the denominator. So it will be 100 over 101. Clear? So that could be one of the very good questions where no calculation is required. Now let's take up a question where the calculation is required. Okay, I would like to show you the solution for our previous question also. Let us see if you have to really calculate and figure it out or prove. Now the question is prove that this is the value. So let us say I change the. Now sometimes sometimes the question could be the percentage error for sine theta for a given value of theta is 1%. Instead of find the ratio, prove the ratio is
100 over 1. 101.
Yeah, the ratio is 100 over 101, right? Because that becomes obvious answer, right?
Right.
So that is how you'll calculate. You say, well, the approximate value of sine theta is theta, right? The approximate value of sine theta is theta. Yeah. Now, if I say 1% error, which is percentage error, right? So I'm writing percentage error on this side. So we say percentage error is 1%. So that means I calculated the value of theta minus sine theta divided by sine theta times 100. That becomes a general equation, right? Now you can cross multiply. So when you cross multiply, you get sine theta here. Multiplying by 100, distributive property, both theta and sine theta. You get 100 theta minus 100 sine theta. Bringing sine terms to the left, it gives you sine theta plus 100 theta equals to 100 theta. And therefore, what you get is the ratio of sine theta and theta is 100 over 101.
Oh, I see. Okay. Just to double check, the approximate value is the value which is on the
X.
y equals x. No,
Y equals.
y equals x graph. Okay, cool.
This is
Yeah.
approximate.
Yeah, and then the sine x is the actual value, or tan x, or any of the other x's.
Yeah, that's
Okay.
sine x. This is sine x. Is that clear?
Yes, yeah. Thank
And the tan x will be going much higher. Let me just use a different color here. Yeah.
Yes, thank you. Yeah.
That is how we are going to calculate. Do you understand the logic? Percentage
Yeah.
error calculation, 1% means what? 100, 1% means 101. Clear. So that is how we will actually work out and find the percentage error in most of the cases. This is actually a very useful example. Sometimes that is also a test question.
Oh, right. Okay.
Yes. Now let's look into example number 2. So here, can you please read the question and try to find the percentage error?
Okay. So find the absolute percentage error for tan theta for a given value of theta which equals 0.173 radians.
Correct. So just do it.
Okay. So we need to do tan of 0.173.
Yeah.
Which is 0.174746.
Yeah.
So that's our
Actual
value.
I should write exact, right?
Yeah. So then we take our actual value.
This is estimated.
Yeah.
So estimated minus exact value divided by the exact value times 100. Simple calculation.
Yeah. So
and what you see is this is
0.73 minus that, and then divided by 0.174746 times 100. Yeah, I got minus 0.999%.
That is less than 1%. Less
Right.
than 1%, correct? Because it was tan, you get minus. Estimated value was lower, right?
Yeah.
Estimated was lower. This is tan, right? And that is theta. This is what we get. Now, you can realize that for theta equals to 0.173, we get only 1% error.
Yeah.
So it's a good data. If the angle in radians is less than 0.173, in that case, you have a calculation which is fair enough because just less than 1% error. You get the idea.
Yeah.
This is a good value to note down. Okay? Similarly, you could also find what could be the value of theta. So you can say, what is sine theta to give you 1% error? That could be your test question. Find theta. So now you know all this. You know the end result, correct? End result will put as 1%. However, the value not known will be this value. So you can calculate that value, correct?
Right, right.
In radians, what could be that value, right? Now, another important thing here is convert this to degrees. 1% error. What is the degree? 0.173.
Yeah.
How much degree?
0.173 times 9.91 degrees.
So 9.9 degrees, I can say. Do you understand?
Yeah.
So almost 10 degrees. So if it is less than 10 degrees, then we can easily approximate using tan theta equals to theta. You get the idea.
Oh, right. Okay.
So if the angle, yes.
Sorry. If you had an angle, how do you know which one to use? So are you saying if it's less than 10 degrees, you use tan theta?
No, I'm saying if the angle is less than 10 degrees, the estimate, small angle estimate of tan theta equal to theta is fair enough. It is less than 1%.
Oh, okay. Yeah.
It may look a huge graph difference, right? So obviously for sine, it is going to be even lesser than this much of error, right? So for sine, we can go for a higher angle, right? So for tan, we just found that for tan, less than 10 degrees is good, right? It gives you less than, it gives you 1% error. Is that clear to you?
Yeah,
9.9. You get the idea. So similar calculation you could do for sine also. So you'll see sine could give you much higher value here in degrees, right?
Yeah.
Now let's look into the third example. So from the examples, we are learning a lot more than what the example is saying. That's the whole idea, right? So
Right.
can you please read this question?
Yeah. So calculate cos of 0.25 to 5 decimal places.
Yes.
Use approximation to find the value of cos of 0.25. And finally, find the absolute percentage error for cos theta for a given value of theta, which equals to 0.25 radians.
Right. So I've done the calculation. So when you calculate the value for cos of 0.25, the exact value is this much.
Okay. Yeah.
And the approximate value is calculated by the formula, which is 1 minus theta square over 2. So 1 minus theta being 0.25, square that and half it, and you get 31 over 32, which is 0.96875. So that is the approximate value.
Right. Okay.
Which is the estimated value, correct?
Yeah. Yeah. Got it.
Now the percentage error will be the approximate value minus exact value divided by the exact value times 100, and you see the result. It is only 0.016% error. You see, so small. Now we are not
Slightly
talking
above
1%. It is
Yeah.
0.01%, 0.02%, you can say, right?
Oh.
And if you convert 0.25 to degrees, it means 14.3 degrees. So even for an angle which is 14 degrees, the error is only 0.02%, you can say, correct?
We could see that from the graph because the cos graph, when you drew it, it was like the time frame of when they overlapped was much longer than the sine and the tan.
Yeah. So
with the y equals x graph.
Yeah, that is what. Yeah. So the sine cosine graph will be kind of like this, you know.
Yeah, like more of it is overlap.
More of it, this whole thing. So they kind of overlap perfectly. So this is like a huge angle in degrees. Is my point?
Oh, I see. Yeah.
So if you are going for just 1% error, this could go to 60 degrees. So for cosine, I mean, it may go to, I mean, for sure 30 degrees, but we'll do a calculation, figure it out. Okay, now another question. So find the absolute percentage error for cosine theta for a value of pi by 6. Pi by 6, you know, is 30 degrees, right? So when you do the same calculation for 30 degrees, you see the percentage error is still 0.358.
Yeah, so much less than like.
It's like you could just use this formula and calculate, correct?
Yeah.
So that is what I'm trying to emphasize, that cost calculation is very, very precise, that error, right? So if I increase the error, right, I want to make it 1%. So I'm just testing different values. That is the whole idea of getting these. So what I did was I increased the radian value to 0.662 radians. Okay. So basically, this is my 0.662 radians. And what do I get? We may have to do this calculation because here I've used cos pi by 6. I've written cos pi by 6. Yeah.
Cos of 0.662 is 0.788.
Okay, that's correct. So this is correct, right?
76. Yeah.
So this is something wrong here. That is correct. Let me just cut this off. Yeah, there have been some. Yeah. And now this is the exact value. Can you do the approximate calculation? 1 minus theta square by 2 uses 1 minus theta square. Theta means 0. I've written here.
Wait, is it 0.662 or 0.0?
Oh, calculation mistake. Can you please do it again?
Okay. 662 squared. Divide by 2, 1 minus that.
Yeah.
0.780878.
Okay, so this is correct, right? So, okay, that's fine. So you get 0.780876.
Yeah.
And when you find the percentage error, calculate this also. It is just 1%. Is that clear to you? Right. So sometimes big errors, however, you get the idea. So what is this 0.662 radians, which gives you 1% error? It is 37.93 degrees. So for 37 degrees, we'll get error which is less than 1%. Do you see that?
Right. Yeah.
So the cosine graph is fairly accurate. I mean, matches with the approximation. That is the whole idea. But
yeah.
the least error you actually get for cosine,
Close.
then it
Yeah.
is sine and then tangent. For cosine, you have, if I look for percentage errors less than 1%, we are looking for an angle which is approximately 37 degrees, right? For sine, we are looking for an angle which is around 14 degrees. And for tan, we are looking for an angle which is about 10 degrees, right? 9.9 we calculate, correct? So, so that is what it is. So if I say that we want to approximate cosine theta for an angle of 35 degrees, can I use the formula 1 minus theta square by 2?
Oh,
You can
sorry,
definitely use because the
35.
error is less than 1%. You get the idea.
Right. Yeah.
Normally, when we calculate these values, let us say we want 1 decimal place answer, the approximation gives you fairly good answer, right?
Yeah. So all of those values that you wrote down, that's for less than 1%.
Less than 1%. Yes.
Yeah.
Less than 1%. Right. So here we have calculated for 14 degrees, right? Now, it is important to understand. Can you please read this question?
Yeah. So find the absolute percentage error for sine theta for a given value of theta, which equals to 14 degrees.
If the angle is given in degrees, first thing first, you have to convert that to radians and then calculate, right? Because theta is in radians. So once you do this radians calculation, that becomes your estimated value. Use calculator to find the exact value and find the percentage. It gives you 1% error, right? 1.002.
Yeah.
So for approximation, for tan theta, we found that the figure is 9.9. For sine theta, it is 14 degrees. And for cosine, it is 37 degrees, correct?
Yeah.
So those are important figures to note down.
Remember, yeah.
Now, so based on that, we have another question. Can you answer this question now?
Okay, so how large can the angle be to have a percentage error of less than 1% in approximating the cosine of an angle?
Yeah, tell me what is
So
the
how
right
large?
Yeah.
34 degrees.
Yes. Do you see that? So that is the test
37 we said.
That is the test question. Now you don't have to do the calculus. You have understood the whole concept. We have seen everything. You get the idea.
Yeah.
So multiple choice test question, you know the answer. For cosine, we'll go for this, right? The
Right.
other angles, we know which one is good for which one, correct? Next
So
question.
sine, we know 14 it is, so 13 degrees.
Correct?
Yeah.
Next. Tangent.
And we know it's 10 degrees, so it's 9 degrees.
Correct.
I'm just telling you the max. Yeah.
Okay, done. So that is how we are going to answer these questions. Perfect.
Oh.
Can you read this question?
So quick. Yeah. So value of the 3 trigonometric ratios is estimated using small angle approximation for an angle of 15 degrees. So arrange 3 ratios in ascending order of absolute value of percentage error.
Yeah. So ascending means increasing, right? So minimum to maximum. So what comes first?
So 15
minimum will be cos, right? And then it will be sine, and then it will be tan. Correct?
Tan. Yeah.
So which one is that? D, correct? You get the idea.
Oh, okay. So we don't need to look at here what is the maximum and everything, because for all of them,
order
for tan, it's 10 degrees max of less than. That's why it's the highest.
For any angle, the error for cosine is going to be much lesser than for
That's
tan,
true.
right? So we don't have to think about it. Correct? Angle could be anything.
Yeah.
What I'm trying to show you is, once we understand the concept, real questions, which are multiple choice questions, could be answered in no time, seconds. You get the idea.
Yeah.
That is what I was trying to emphasize. Can you please read and answer this question?
Yeah, so percentage error for estimated small angle approximation for sine 10 degrees, sorry.
Will be, what is the correct?
So it would be positive less than 1.
Yeah.
B.
So it is going to be, because estimated is this, right? Actual is this. So it is always positive or negative?
Positive. No, wait, let me think. Sorry. So
this is the estimated, right?
Positive.
It is going to be positive.
You paused, so it made me question myself.
And 10 degrees means less than 1%, correct?
Yeah.
So it is positive and less than 1%.
Then B. So you can't do the pausing because you make me question myself. I was really thorough. Yeah, yeah.
You get the idea.
Yeah.
Actually, it is a very complicated question. Is it less than 1%, more than 1% for sine theta? We know that sine theta 14 degrees work for 1%.
Yeah.
Right?
And
So
anything
10 degrees
down.
means we are safe. We are below 1%. So we don't
Yeah.
have to do any calculation. Otherwise, if you don't know it, then you have to do a calculation, right? You say, well, it is 10. I mean, first is degrees to, you have to convert to radians, first things, and then you do the work. I mean, you're gone,
Oh
correct?
my God, that's going to take so long, especially in time conditions. But at least I know both ways. Like I do know how to do that by calculation. But if you can just look at it and know, that's so much easier. Oh my God.
You get the idea. That is what I was
Yes.
trying to teach you today's lesson. Well,
Oh,
you
wow.
could use the calculator. The whole idea is why I am actually not really in for this chapter. See, when we are estimating, we are actually not using a calculator. If you have a calculator, why will I estimate?
Oh my God, that's so true.
So
Because
the
if you have
chapter
the
on
calculator, then
percentage
find the
error
actual
makes no
ones.
sense to me. Yes, chapter on small angle
Oh,
approximations make sense. You get the idea.
yeah.
If you want to calculate the percentage error, you have to calculate the actual percentage. If you have to calculate the actual percentage, why will you do percentage?
Yeah, because you're already finding the actual. So why am I doing all of this?
Correct. So why am I doing is being answered like this to get an idea how accurately we are estimating, right?
Oh, okay.
So
Got it.
just is that if you are interested in 1% or low, right? 1% or low, in that case, for cosine, we could go for an angle as large as 37 degrees. For sine, let me write sine first, right? We could go for 14 degrees, and for tangent theta, we could go for 9.9 degrees, right? I don't want to write 10. You get the idea. Secondly, what we understand here is that whenever you are estimating in that case, for tan, the answers will be negative, right? Because this graph is above the x value, right? So this will be negative, and for these two, it will be positive. Is that okay? So that is why I feel this particular question, which I've put here, is a very relevant question. So the whole exercise of calculating the errors and the percentage errors is to understand how accurately are we estimating, right?
Oh, makes sense.
And when we estimate, are we estimating higher or lower? We should know that, right?
Yes, yeah, definitely.
We should know that. If I know that my estimated value is higher, I can round lower to get more accurate result.
Yeah, yeah.
You get the idea?
So it's good to know that. Yeah.
Round lower. If I am estimating already lower, I would actually increase so that I'm closer. You get the idea?
Yeah, yeah, yeah.
So that is a very good thing to learn from this particular chapter, not just calculating with the calculator the percentage error. You get the idea?
Yeah. I like what you've done with it. Yeah, it makes more sense to me because I tried it for my book. Obviously, before you taught, I just thought it would be simple, but it wasn't. I was getting all my head like really twisted around it, and I just think the graphs you've drawn are just so helpful because for every question, all I'm doing is picturing that graph on the left-hand side.
Yes.
It's so good, like honestly. So like the ones in my book are just absolute confusion.
These graphs are pretty good actually. So
really
keep them in mind. You know, this is very useful.
Yeah, I am.
So
that's why it's so helpful.
From this graph, this is a very good graph. You can always estimate, draw a line, for example. You know, well, estimate is here, right? This is my estimate. So when I find percentage error, I'm estimating lower for tan, estimating higher for sine, estimating lower for cosine, correct? Sine, cosine, lower. Simple as that. And that helps us to like, clear all these things in your mind. Put them in your mind. I mean, you don't have to remember most of the things. You can also see how closely the cosine function is, right? If it is so close, obviously we have a very good estimate, right? If it is like this, we don't have a good estimate.
Would there ever be a question where they give you like an angle and say, I don't know, like, can you get it so close to like cos, tan, or sine? Or do they always tell you which one they want you?
They will tell you which one, right? They will tell you which one, correct? Because the first thing is calculation is required for cos theta. It is 1 minus theta square. Now,
Yeah.
in radians, we are looking at an angle, which is point, let's say 065. Now doing square of that is not an easy job, correct?
No.
It's
No.
easier is to find the cos of that.
Right. Oh, I see. Okay. Yeah.
So as
Makes
far
sense.
as the cosine estimate is concerned, I agree it is very accurate, but again,
Yeah.
you need a calculator to estimate.
Yeah.
What's the whole
Even
point?
to estimate. Yeah, that's true.
Anyways, academic importance. So let's
Yeah.
leave it there. So we'll close the lesson here today. I hope you have clearly understood this topic, right?
Yes, it was so clear. I'm actually kind of excited to try my questions from the book, because as we went through them, the questions were getting harder. But I was finding it easier to answer them, because more and more the concepts were making sense, and especially that last one with the positive and then less than 1%. We didn't do any calculations, but the calculation that's required without knowing this concept is like long. Like we talked about the conversion to radians, then using that formula with the approximate, take the actual, and so all of that, when you can just look at it and see it's 10 degrees, less than 14. Okay, it's going to be less than 1%. It's just so good. Yeah. So thank you, sir. That was so helpful. Like, genuinely, it's not going to go from my mind. It's going to be there.
Correct. So we'll continue with trigonometry in the next class. We'll look into simple harmonic motion. Yeah, that's a we'll actually look into the compound angles. What is sine of a plus b, cos of a plus b, and things like that.
Thank you.
And then get into that compound angle formula with trigonometry. Is that okay?
Yeah, sounds good. Sounds really good.
Enjoy your weekend.
Yes. Thank you, sir. And you. Have a good one. Bye.